Section 35.10 Reversible Reactions and Equilibrium. Now let's look at this chemical reaction mechanism. There are two elementary reactions. One is from A to B, the other is from B to A. They have different reaction rate constant. And then we can write out one differential equation for each species. For A, you have dA over dt is equal to Kb times B minus Ka times A. This is positive because A is produced in the second step. The second term is negative because A is consumed in the first step. That's why. And you can write out a similar equation for B. Again, B is produced in the first step and it's consumed in the second step. Both elementary reactions are going on at the same time. At equilibrium, the reaction rate of the forward reaction from A to B is equal to the reaction rate of B to A. And that's a so-called dynamic equilibrium. Assuming at time 0, we do not have B in the system and A is A naught. And then we have this equation, B is always equal to A naught minus A. Again, to produce 1B, you have to consume 1A, and that's why. So A plus B is always a constant. You can also prove that by adding up these two equations. If you add up the left-hand side, you will get dA plus dB over dt. If you add up the right-hand side, you get 0. So this and this cancel, this and this cancel. So it tells us the sum of A and B does not change with time. A plus B is always a constant, and at time 0 the sum is A naught. Now we can solve the shown equation by replacing B with A naught minus A over here, and then we got this differential equation to solve. It contains only two variables. One is A, one is time. So it's possible to solve this differential equation by simply separating the two variables. We can move this dt to the right hand side. We can move this expression of A to the bottom of the left hand side, and then we integrate both sides. We get this expression. It looks very complicated, but we can verify this equation for time 0 and time equals infinity. So we plug in time equals 0 right here, and then this exponential function is just 1. And you have Kb plus Ka over Ka plus Kb. That's just 1. So at time 0, A is equal to A naught. That's correct. What about T equals infinity? We plug in T equals infinity. We get the concentration of A as well. It's going to be Kb over Ka plus Kb times A naught. It still looks complicated, but there's a reason. If we look at the concentration of B, the concentration of B is A naught minus A. So we simplify this expression by combining these two terms. We get this expression for the concentration of B. And then if you look at this one, you'll realize that when we plug in time equals 0, you get Ka minus Ka on top. So the concentration of B is 0 at time 0. You can also plug in time equals infinity. And then this term is 0. The second term on top is 0. And then you get Ka over Ka plus Kb times A naught. So you get the concentration of B similar as the concentration of A when time is infinity. The difference is this. For the concentration of A, you have Kb on top. For the concentration of B, you have Ka on top. So we can see these two equations are the equilibrium concentrations of A and B. And then the equilibrium constant is B over A. And then if you do B over A, it happens to be Ka over Kb. And it does make sense. Why? Because again, at equilibrium, at the dynamic equilibrium, the forward reaction rate is equal to the reverse reaction rate. The forward reaction rate is K sub A times this concentration of A. The reverse reaction rate is K sub B times the concentration of B. And at equilibrium, this Kb times B is equal to Ka times A. And again, this K sub Eq, this uppercase K sub Eq, is the reaction rate, is the equilibrium constant. Ka and Kb are the forward and reverse reaction rate constant. And the forward over reverse is the equilibrium constant. The equilibrium constant is also the concentration of the product divided by the concentration of the reactant at equilibrium.